Hello, everyone. Thank you for joining us again as we continue to look at some of the works that Uhlenbeck did and related topics in Yang-Mills theory and harmonic maps. We just spent some time looking at harmonic maps in order to motivate some of the techniques that Uhlenbeck used. Now I'm pleased to have, well, we're all pleased to have Stefan with us, who's going to look again at the Yang-Mills equations and see what we can do with those. Thank you, Stefan.
Thank you, Tim, for the introduction. All right, so as Tim mentioned, I guess it's been a couple of months since we looked at Yang-Mills theory, so I just want to remind, I guess, so reminder, what actually are Yang-Mills equations and Yang-Mills functional and so on. Just quickly go over it. And as always, if you have any questions, just please feel free to interrupt and ask on whatever. All right. So what's the data? What are we given? Well, we have a principal bundle over some Riemannian manifold. Let's say M is compact and orientable, just so I don't have to care about it. And this is G principal bundle. And again, assume G is compact so that we have negative killing form and we don't need to care about that. All right. So when we are given such a G principal bundle, we can talk about connection. So we introduced at some point connection form. Connection form is a form, one form to be precise, on the bundle P with values in G, where G is the Lie algebra of our group, and it is G invariant, right? And the best thing that our connection form gives us is the exterior covariant derivative, something I'm going to denote dA. So what it is? Well, it acts on any K forms on P with values in any vector space, where this vector space has some action of our G. Let's say I'm going to talk about just G invariant K forms. And it maps these guys to K+1 forms on P, values of G, which are again G invariant. Sorry, values in V, which is some vector space. But furthermore, they are now horizontal. So what does it mean? Remember that when we have a connection or connection form, we can think of it as horizontal distribution. So we can have functions which just care about the horizontal component, right? The forms on P that care only about the horizontal component. And how does this dA work? Well, essentially, it's the usual exterior derivative D, except before applying, we first apply the projection to our horizontal component. So you can loosely think of it as decomposed the projection, maybe projection to horizontal component, right? And that's why we get the to horizontal forms now. Well, what's the beauty of this? Well, the beauty of this is that when you have horizontal K+1 forms, which are G invariant, they are actually isomorphic to the two forms, but this K+1 forms, but this time on the base manifold M, essentially because of the G invariance and the fact that the form is horizontal, we can just pull it back to just the base manifold. And so it's K+1 form on M with values in some adjoint bundle to P. Let's say this is rho, and by rho I mean the function. Rho is the action of G on our vector space, right? So essentially, having a connection one form induces exterior covariant derivative, which gives us a way how we can differentiate bundle valued K-forms as long as the bundle is associated to the original principal bundle B. Okay, I hope this makes sense. So a kind of special case of this is we can apply dA on A itself, because A is bundle valued one form. And what we're gonna get is something which you usually note FA. Probably during this talk, I'm just gonna drop the A and just write F for this thing. And because I just don't write, I don't want to write too many A's. And this is called a curvature form. So this is two form on P with values in G, the algebra of our group, which is G invariant and horizontal. In other words, it's a two form on our base manifold with values in the adjoint bundle. Okay. That's clear. So what is actually the Yang-Mills functional? Just reminding, Yang-Mills functional is a functional on the space of all connection forms, and it's given by an integral over M of the curvature form. Now, here's a small note. We need a metric, because otherwise this expression doesn't make sense. So we need a metric on here. So let me write this thing explicitly. This is actually isomorphic to sections of second covariant derivative of the cotangent space, tensored with at P, right? Just by definition. On here, we have metric induced by the Riemannian metric G we have started with from this metric G. But we still need a metric on the at P, and usually we just choose the negative of the Killing form, but any at invariant inner product on the Lie algebra will do. So really, this form, this norm is with respect to something like this. All right, this is the Yang-Mills functional. And we've seen in some of the previous talks that this induces, or I guess I'm going to write it below. This implies that we have the Yang-Mills equations, which are essentially Euler-Lagrange equations for this functional. And they are quite simple to write. They are just dA star of FA equal to 0, where dA star is the adjoint of the exterior covariant derivative we have defined earlier with respect to precisely this metric, which I just talked about. Right. Makes sense. Also, what we had last time, or maybe not last time, but in some previous talks, there were Bianchi identities. Which are going to be important today as well. So what are the Bianchi identities? They're essentially just an equation that the exterior covariant derivative applied to FA is 0. Right? Maybe you might think that this is obvious because it's dA of A, but the exterior covariant, it's not, maybe it's not true in general that dA composed dA is 0. This is not true. Right? So this is meaningful identity, so to say. Well, and this altogether should seem quite familiar, because when we talk about harmonic forms, there's also some differential and the adjoint, and we require similar conditions. So in the spirit of harmonic forms, let's say, we can define the associated Laplace operator. I'm just gonna define it as dA star dA. Yeah, I was writing dA as the upper index plus dA star. So now we can talk about Yang-Mills equations in a sense that the associated Laplacian of Fa is 0.
The sound's gone, I think.
Stefan, are you still there? Possibly some connection issues. Perhaps we'll wait a couple of minutes to see if he makes a grand return. Haven't heard from Stepan yet. I've almost found his phone number and I'll give him a call to see if he's around and is struggling with connections. Maybe sit tight for a couple more minutes. Stepan is here apparently, but some significant connection issues, it seems. I've asked him to reconnect and join again. It sounds like he's been speaking to no one for the last 5 minutes. So hopefully he'll come back soon and rectify the situation.
Hey everyone, sorry, I have no idea what happened. Can you hear me now, I guess?
Yes.
All right. So, sorry about that. I can start sharing again. All right, can you see the screen?
Yes, can see the screen.
Okay, so what was the last thing you heard?
Laplacian of A of f of A is equal to 0.
So this?
Yes.
Right. So sorry about that, let me continue. So another thing I mentioned is that Young-Mass equations are gauge invariant. So I was reminding what is a gauge group. Those are essentially all automorphisms of our principal bundle such that the automorphism covers the identity. So it's this commuting triangle right here. And because of this gauge invariance, these equations are not elliptic. And we can't apply the usual theory. So one of the big results from Uhlenbeck was Coulomb gauge, or so-called gauge fixing, which was done by Vishnu, I believe, 4 seminars back, or something like that. And so I just stated it. It's just that you can have a P between 1 and n, and then there exist some constants, epsilon and c, such that if we have our connection with a bounded curvature, there exists a local gauge transform, which you can imagine as some sort of local trivialization. And A star is this connection in this local trivialization. And the claim is that in this nice trivialization, we have this extra condition, d star of A equals 0. We have some other conditions such as that A vanishes on normal vectors to the boundary. And also we have some bound on our P1 norm in these local coordinates. But really, the important part is this one right here, the extra equation, which kind of destroys the gauge invariance and restores, or so to say, restores ellipticity. So we can use our elliptic theory. So yeah, that was pretty much all from the reminder. Can you still hear me?
Yes.
Yes.
Yes, thank you. I guess I'm gonna periodically ask so that I know I'm still in the Zoom. All right. Are there any questions to the reminder, or can I move on to the new stuff? All right. Seems like not. Okay, so what I want to start doing today is the removable of singularities for Young-Mills equations. So just I'm gonna very vaguely state it as the goal. So the goal is to have a Young-Mills connection. Sorry. If we have Young-Mills connection over a punctured ball in dimension 4, I guess that's another remark right here why we are talking about dimension 4. So if you look at scaling invariance of your Young-Mills energy, that was Young-Mills energy was just the Young-Mills functional, and you look at scaling invariance, what's gonna pop up is the factor of rho, which is the change of scaling, to the 4 minus n. So the dimensions, similar as with harmonic maps, where the critical dimension was dimension 2, and the harmonic maps were conformally invariant. So in our Young-Mills theory, the critical dimension is dimension 4. That's why we're gonna focus on that, where the equations become, again, scaling invariant. Right? So just to remind, we have Young-Mills connection over punctured ball in dimension 4. We have also bound on the L2 norm of our curvature. And we want such connection to extend to a smooth Young-Mills connection over B4, over the whole ball, basically. I don't want to make this precise yet because I'm not gonna prove this today, but that's like the goal we are going for. We would like to remove singularities. And I'm gonna also mention this is analogous to a theorem which was done by Brett, I believe, in one of our seminars, which is again very vaguely, if we have F from some punctured disk, a Riemannian surface, and it's harmonic, and also the energy is bounded, similar to our case, then F extends to the whole disk. All right, so this was theorem, which is proven in this seminar by Brett, and this is obviously an analog in dimension 4 for our Young-Mills connections. And for this, we're still following the Donaldson survey of Uhlenbeck's work, and also a paper by Karen Uhlenbeck, which is called, I believe, Removable Singularities. It is in Young-Mills fields. Right. So let's get to it. So we're gonna start with something like a small energy estimate, which was similar, or a small energy theorem, rather, which is again analog to one of the theorems about harmonic maps in small energy.
So maybe a quick comment.
Yeah, sure.
The paper by Uhlenbeck that you just quoted removable singularities in Yang-Mills fields. In the initial discussion, he says the proof of the removability of singularities in the Yang-Mills case in dimension 4 is remarkably similar to the proof of the removability of singularities of harmonic maps contained in Sachs-Uhlenbeck. Written about the same time.
Thank you for the remark. All right, so I'm gonna write the theorem, the small energy theorem, which we're gonna hopefully prove today. So it goes like this: there exist epsilon and c bigger than 0, such that if A is Yang-Mills connection, over a unit ball, one, as I mentioned, we're going to do it in dimension 4. And let's denote E our energy, our Yang-Mills function. I guess I was writing it as Ym. So just a reminder, this is the integral. I'm just gonna write F for curvature from now on. So if the Yang-Mills energy is smaller than epsilon, then the norm of the curvature is less than or equal and times some c times epsilon. Sorry, not times epsilon, times E, times the energy on some smaller ball, let's say with half the radius. And this is pointwise estimate, not on the integral. So again, this should sound very similar to one of the theorems from harmonic maps. It's pretty much the same statement. Okay. So Donaldson in his survey mentions that it is possible to prove this by cage fixing and continue with like pretty much the same way as we did for the harmonic maps. I haven't done that, so let's say this is exercise for anyone who's interested. And we're gonna follow the Uhlenbeck's proof, which is a bit different and introduces some new techniques which are, I guess, valuable to learn.
So this is a 4-dimensional theorem, right?
Yes.
Whereas the harmonic map epsilon regularity case was for arbitrary dimension.
Yes, that's true. But you can actually, it's possible to prove this. And I think in the paper by Uhlenbeck, she actually does this for arbitrary dimension. But since we're focusing on the removable singularities in dimension 4, we can just state this in dimension 4. And the proof is, I believe, a bit easier. Yeah. All right. So let's go with the proof. All right. So as I mentioned in the reminder, we know that F is harmonic. That's because like F is coming from a Yang-Mills connection, so it must have harmonic curvature. But actually, there exists another Laplace type, let's say, or Laplace operator, which we're gonna denote nabla squared, right? So how does this work? Why there is a second Laplace operator? I'm gonna draw a little diagram. So we have our two forms over M with values in the adjoint bundle, right? Which is the same as having sections with second exterior power tensored with adjoint P, right? So down here below, we can move, let's say, to free and so on, to free forms using our exterior covariant derivative, also for one forms, right? And we can move backwards using our codifferential or the adjoint to exterior covariant derivative. And all of this is coming from the connection on the principal bundle, in this case from Yang-Mills connection. However, that's essentially a connection on this part. However, we have another connection on a tangent bundle because we are over Riemannian manifold. So essentially, here we have connection A, and here we have our connection Levi-Civita coming from the metric because we are over a Riemannian manifold, right? So the idea is that we can tensor these connections together and get the connection on this tensor bundle, and that's exactly what our covariant derivative will do. So it will move from these sections to a sections of the same bundle, but tensored with T star M. I guess maybe it's better to write it in a different order. Right? So it still has, it takes still free inputs and it's still bundle valued, but now we didn't do the anti-symmetrization. We didn't get to forms, so to say. So sometimes this is called a rough Laplacian. And again, it has adjoint because we have metrics on this on these bundles, right? And the interesting part about this is that both the Laplacian, which is kind of the Hodge Laplacian coming from the connection, and the other Laplacian, which is the rough Laplacian coming from the tensor connection, they have the same principal symbol, and then only differ by a zero order term, which is very interesting. Does this make sense? And am I still on the Zoom?
Yes, still here.
Yeah, thank you, Tim. All right. So we have the two Laplace operators, and it was proven, I believe, by Jean-Pierre Bourguignon and Lawson that there exist. Write it in here. That there exist Weizenbeck formula relating these two operators. So, Weizenbeck formula. So I'm gonna state it over flat manifold, just as Karen Uhlenbeck does. She mentions that the lower order terms, which are some Ricci curvatures, don't matter in the final computations. I haven't tested it, but I believe her. So let's say we have phi, which is a two form with the value in the adjoint bundle. And what we get is that the Laplace coming from A of phi minus the other Laplacian operator I just defined is equal to this special bracket, curly bracket, which, as I mentioned before, is zero order operator. So this is zero order. And I don't want to get too much into details. How do we define this bracket? Because I don't want to, that would take too long, but essentially, locally, one can write the bracket as some sum over J with coefficients, and using the bracket in the fiber, because our fiber is Lie algebra, so we have a bracket there, and we can use a bracket. So like this, and there are some indices. Hopefully, I think JK, and this is JKJI, I believe. Yeah. So locally, this bracket IK. But that's not really important. The point is that it's some zero order operator, and we know how it looks like.
Another comment, if you don't mind, remark.
Yeah, sure.
That term for the Weizenbach formula over a flat manifold, when Dirac worked it out for his Dirac operator on spinners, with the under electromagnetism, so it's a U1 bundle. He got the immediate consequence of that right-hand term is that there's a spin, there's a anomalous magnetic moment and a spin on the electron. So that right-hand bracket is basically forces you into an anomalous magnetic moment for the electron and the spin a half for the electron. Yeah. So
it's very interesting. Thank you for the comment. Didn't know that. Yeah. Yes. So basically, where we're gonna use the Weizenbach formula is for phi equal to f, because as I mentioned a couple of times today, Laplace A of f is equal to 0, because we are dealing with Yang-Mills connections that have harmonic curvature. So the Weizenbach formula becomes, just the rough Laplacian, or minus the rough Laplacian, is equal to f with f. So we have a way how to translate second order operator into zero order operator, which will be useful. And also, maybe I'm gonna denote this star. And also there's a straightforward estimate you can do, which I'm not gonna do as well. That if you look at the norm of this curly bracket, I think it's more than 4 times the square norm of the curvature. So I guess I'm gonna use double star. I'm gonna use this as well. All right. So this was Weizenbach formula. And now we can get to the proof. So basically we wanna work out some estimate. Ideally, we wanna have some estimate on the minus of Laplacian, our f, by something, let's say alpha here, c here. And this estimate would enable us to like reduce the order and work from there. So how we're gonna get there, this is just straight out computation. So I'm gonna write it for a general phi, which is a 2 form with the values in the adjoint bundle. So that you know I'm not using any properties from the curvature. I'm going to do that only in the last line. So we're essentially looking at Laplace on size of phi, no, psi, whatever. So this is just 2 Laplaces on psi multiplied by psi plus 2 covariant derivatives of psi, right? So a product rule. And so from this, we can write psi Laplace psi is equal to 1/2 of the Laplacian, but I'm going to do trick here, and I'm going to write it as part of the Hodge Laplacian, because these are just functions, and on the functions is the same. Minus d psi squared, where I just switched from covariant derivative to d, because again, on functions they are the same. All right, should be it. Okay, continue the equation. So this is 1/2 d star 2 covariant derivative of psi. I'm gonna leave this term b for now. All right, so obviously the 2 is gonna cancel out. Now we are left with d star, and d star x, just let's say we choose some local frame xi, and we're gonna be left with xi, covariant derivative along xi on psi, both terms, plus actually I'm gonna just write it in the different order, sorry, just so it's clear what I mean. So it's twice on the first one, plus this, and again minus the term d phi. So if we sum over xi's, and I remember we are over flat manifold, so this is just the second operator on psi, like the rough Laplacian psi, plus covariant derivative of psi, like the norm of covariant derivative, minus d on psi squared. And now I believe this is called Cato's inequality. Essentially, this thing's positive, like the norm of the covariant derivative is higher than the norm of the differential of the norm. And we're gonna end up with just, so I think this is called Cato's inequality. And we're gonna end up with a rough Laplacian of psi on psi. Right? Hopefully that makes sense. I'm running out of time, so just gonna, right? So now we're gonna substitute, instead of psi, we're gonna put our curvature. So the inequality goes from here to here. And we're gonna end up with size of our curvature, so Laplace is greater than equal than the rough Laplacian on f, sorry, on the size of f. No, on f, right? With f. Now we're gonna use our star right here, right? So this is equal to minus the curly bracket f with f with f. And now we can use the kind of the Cauchy-Schwarz, but we have minus here, so it's gonna be minus bracket ff times this norm of f, and now we can use double star right here to get to minus 4 f cubed. So if we assume f is nowhere 0, which I believe there are ways you can deal with it if it is 0, you're gonna essentially get Laplace on f is greater than or equal than minus 4 f squared. Right. Or in other words, let's see if I'm gonna change the minus sign. Minus Laplacian is more than 4 f squared. Does it make sense? Am I still here in the Zoom?
Yeah, yes.
Still here. Yeah.
Okay. So yeah, we have, I don't know. Can I have 5 more minutes, or should I? I think it should
How
be
much more
15.
material do you have?
Not much. There's actually I don't quite understand the last argument. So there's like one integration, and then the argument I don't understand. So
Okay, yeah, certainly keep going for another 5 minutes, and we'll see how you go.
okay. So now at this point we can define chi, our cutoff function. That's where the smaller balls come from. Remember, we get the estimate on a smaller ball than the initial one. So that's where this comes from. So let's say cutoff function on b 3/4. By that I mean it's 1 on b 3/4 and goes to 0 before reaching 1. Next, multiply by chi squared f and integrate over the whole ball before. So what we're gonna get? We're gonna get minus integral of Laplacian f times chi squared norm of f, right? Here we can straight apply per partes, and we're gonna get to integral. Yeah, I'm integrating over before the ball. Yeah, radius 1. I didn't write it, but I mean the ball of radius 1. Otherwise, the kind of function will be kind of useless. And this is the derivative of the norm and the current derivative of chi squared of f. And this is smaller than or equal our right hand side, which is 4 integral over chi squared of f cubed. Again, over d1. Right? So here just there's this inequality, equality, there's some identity that works. You can check it again. So it's gonna state it. It holds that this guy on the left-hand side you can expand into something like this. So the covariant derivative of chi of f squared minus covariant derivative of chi squared f squared. And if you apply this equality, what you get is integral over just the norm IF squared is smaller and equal than the part we had before. So that's chi squared F cubed. And the extra term coming from here, which should be the integral of chi squared. Right. So hopefully this makes sense. And we see that now we have bounds on L2 bound on our IF, right? And there's Sobolev embedding into L4, and we can apply Hölder inequality plus rearranging to get L4 bound on chi F. Chi's norm of F, which means this should be L4 norm, L4 bound, on chi of F. Of just F on smaller ball, so on the B 3/4. And I don't really understand how you proceed from there. I was sitting here last night and just couldn't figure it out. So Donaldson just mentioned that you can apply this iteratively, and I don't really know how to get higher and higher bounds until you get to L infinity bounds, which is essentially point estimate, which is what we want. But that point I still don't understand. So hopefully I can figure out till next time, and then I'm gonna present it then, I guess. So yeah, that's all for me for today.
Thanks very much for that, Stefan.
Stefan, are you following Uhlenbeck's 82 paper? And if so, whereabouts is this step that you're saying that you're not sure?
Yeah, so Uhlenbeck does this a bit more generally. She assumes less regularity, and in her 1982 paper, she does it more generally. So I was following the Donaldson survey of Uhlenbeck's results.
Right.
I can, I guess, show it to you.
So yeah, so I can't see in Uhlenbeck's paper.
Yeah, it's right here in the Donaldson survey.
Donaldson survey paper on.
Can you see the document now?
Yeah, what page is that? 42 or so.
42, yeah.
Okay, thanks. So I'm a bit puzzled about the epsilon regularity that I mentioned before, because in Uhlenbeck's paper, she specializes to 4 dimensions in her section 4, and her theorems in section 3, 3.5 and 3.6 have norm FQ less than infinity, effectively for Q greater than or equal to n over 2. So this is Uhlenbeck, is it? Yeah, 3.
Yeah. I'm just
3, 5, and 3, 6.
Sorry, which page?
Yeah, 23. Yeah, keep going. Theorem 3, 5, and 3.6.
Yeah.
So the assumption here is it's the n over 2 norm is less than the constant, not the L, not the L2 norm.
Yeah, but I mean, my n is 4, right? I mean, 4 dimensions.
No. That's true for. It's when n is 4, which she specializes to in the next section. Yeah, but these theorems about epsilon regularity, works for n equals 4, but the assumptions are the ln over 2 norm is small, so it doesn't work for higher dimensions. In harmonic maps, the hard part was getting a epsilon regularity theorem for the energy of the harmonic map in arbitrary dimensions, right? If the L2 norm of the energy was really small,
and
dimensions,
so
then it was
here's
the harmonic map was smooth. Yeah, and that's the thing that's missing, I believe. It's that epsilon regularity where you replace n over 2 here in the assumption with 2 for arbitrary n bigger than 4. I think it's exactly that epsilon regularity, I think, is what's stopping getting the the partial regularity of Yang-Mills up to the n minus 5, n minus 4, and then
it's
dimensional extension up to n minus 5 regularity of Yang-Mills, which is still to appear in full generality. That's what I was trying to do in 82, but I couldn't get the epsilon regularity. So
I see.
So yeah, see, I think as far as I know, the equivalent, replacing n over 2 with 2 there in theorem 3.5, I think that's the epsilon regularity result that hasn't been achieved yet.
Oh, I see.
Could easily be wrong with that, but that's one comment. Another comment is there's a paper by Penny Smith and Karen Uhlenbeck called Removability of a Codimension 4 Singular Set for Solutions of a Yang-Mills Higgs Equation with Small Energy. And I'm pretty sure that's the L2 energy. I haven't read this paper, but I've looked at it a bit.
Sorry, what did you say was the name of the paper?
It's by Penny Smith and Karen Uhlenbeck. And it's called I don't know what date exactly for archive, but it was copyright 2021, International Press. Surveys in Differential Geometry 24. And the title is, so it's a higher dimensional version of what you've just done. Removability of a codimension 4 singular set for solutions of a Yang-Mills Higgs equation with small energy. So I think Yang-Mills Higgs or Yang-Mills on its own is, I think this includes the Yang-Mills on its own. But
I think it should, but I'm not sure either.
Yeah, not certain. Yeah, so
thank you for the reference.
That's probably post Donaldson. Certainly post Donaldson's first review. What's the date of Donaldson's thick paper that you're dealing with?
It's on 22.
22, okay, so he should have seen this 21 paper of Karen Uhlenbeck's, I guess, which probably had a much earlier archive version. Anyway, it appeared to be a higher dimensional version of the 82 result.
Okay.
Thanks for that discussion. Are there any further comments or questions that anyone has for Stepan or for Peter for that matter? All right, then thank you all for coming, and let's thank Stepan again for giving us this talk.
Thank you.
All right, thanks everyone. I'll stop recording now.
Thanks, Stepan.